After looking at the examples for the bottom up approach for heap construction, we shall now look at the algorithm for the bottom up heap construction. Okay. So, in order to understand the algorithm, we shall understand the steps in the algorithm with our previous example. Okay. So, consider the previous example. These are the elements 10, 20 up to 18. Then this is the very first full tree that we construct, and there are 7 number of nodes initially. Okay. So, just for the sake of understanding, I just write the indices of these elements here. Okay. Indices of these elements. Done. Okay. Now, from where did we start the algorithm? We started building the heap starting from this node, isn't it? So we considered this node. Next, we compared these two, I mean the children of this node, and the maximum out of them we compared with this node element, and if at all that maximum element is greater than the node under consideration, I mean the parent, then we exchanged, isn't it? So basically, if you at any point in time, it requires total 2 comparisons. One comparison is to compare among the children, and another comparison is to compare the child against the parent, isn't it? Okay. Therefore, so we have to start from this node. Okay. Can you just recall the properties that we discussed prior after the definition for heap? Yeah. So if you have the array implementation for the heap, the first n by 2 elements will form the parental nodes. Yeah. In this case, we have n is equal to 7 elements. So 7 by 2 floor value, it is 3.5, I mean 3. So starting from, till the index 3, we have all the nodes as parents. So we have started with the indices 1, 2 up to this index, we have the parent nodes then, isn't it? Therefore, if at all we have to start the construction of heap, it has to be from this parent node, and which is available from this n by 2 floor function, isn't it? Therefore, you can look at the algorithm, bottom up algorithm. The algorithm starts from for loop for I is equal to n by 2. Why I is equal to n by 2? Because we are starting from the last parent. The last parent is available at this index, and this index is available with this formula n by 2 floor function. Okay, right. So till what value? So for loop should run from 3, then for the index 2, and then for the index 1. Therefore, for n by 2 floor down to 1, I mean I value takes from 3 to 1, that is the meaning. Do. Okay. So this is the very first statement in the algorithm. Why? We are running the algorithm for all the parental nodes. Okay. Done. Next. So let us call this index that we have considered as the index k. Okay. So let k is equal to I, and let this element v is equal to the array he is considering array to be h. Okay, array h. Therefore v is equal to h of k. V is equal to h of k. What does it mean? So initially, so I will write the values here. So initially this k value is equal to 3 and v is equal to 15. That is the meaning, because we have to consider the element at this index. Index is 3, element is 15. K is equal to I, index is k, element is v. Okay, right. Next, we take one more variable called as just heap, and we initialize it to false. So this variable is required just to know whether all the heaps that we are constructing are actually the heaps, that we will come to know when we exactly trace the algorithm for element at index 1. Okay, right. Heap is equal to false. Now what we have to do is we have to check this element against these children. After that again we have to move down, isn't it? So if at all you are starting, you are at index, this index, we have to check against these two, and again we have to check at this level, isn't it? Therefore once again we should have one more loop here. What is that? While not heap, while not heap, until and unless we are not finding the heap in the subsequent levels. And the thing is we should not reach the leaf nodes. Okay, so how do we come to know that we are crossing the leaf nodes? Okay, so see here, initially what we are considering is k is equal to 3, isn't it? Okay, k is equal to 3. Now where is the child, where are the children of this node? The children of this node are present at this index and this index, and we know that given an index I, the children of this element are given by 2i and 2i plus 1, isn't it? Therefore if you consider the left child, that is 2i, it is 6 in this case, in this example 6. Whether this 6 is a valid position, how do you check? Yes, in the diagram we will come to know this 6 is a valid position, but how do we come to know? This index 6 is less than the maximum elements, isn't it? The given n value. Therefore if at all this 6 is less than or equal to the maximum number of nodes, there is some node, right? There is some node. Okay, and how do we obtain this 6? It is 2 into 3, and this 3 is nothing but k. Therefore 2 into k less than or equal to n. So if at all 2 into k less than or equal to n, yes, we have still the tree. Therefore while not heap and 2 into k less than or equal to n, less than or equal to n, what we have to do? So first we have to consider the child of this node. So the left child of this node can be obtained by j is equal to 2 into k, right? So once you obtain the left child node, we have to check whether there is a right child that is present. How do you check that there is a right child present? Suppose in this case suppose in this case this element is not there, 18 for example. So in this case n will be 6, total number of nodes. Therefore 2 into 3 will be 2 into 3 less than 6. Is this condition true? No. This 6 is the last element, and 6 less than 6 condition fails. Okay, therefore provided j is equal to 2 into k, if j is less than n, what is the meaning? If 6 is less than 7, that means 6 is there and 7 is also there, condition true, that means both the children are present. Therefore if j less than n checks that there are two children, okay, right? So if there are two children, what we have to do is we have to find the maximum among them. Okay, so currently j is pointing here at 25, j value is 6. Therefore we have to check whether this right child is greater than the left child. Therefore, and that checking is to be done only if there are two children, and if j is less than n, there are two children, and if h of j is less than h of j plus 1. What does it mean? So j is the left child, j plus 1 is the right child. If right child is larger than the left child, then we have to change j is equal to j plus 1. In this case, suppose this element is greater than this element, then we have to change j to 7. So that is the meaning. So if h of j less than h of j plus 1, then j is equal to j plus 1. Done? Okay. And why we have to do that? Only if there are two children. Okay, done. Now with this you found the larger child. Now you have to compare that larger child, I mean the element which is present at index j, against v, because v is the element that we are considering at this position k, right? Therefore the next comparison is if v is greater than or equal to h of j, we have to compare v and h of j. So is v is greater than h of j. What is the meaning? V is this element, h of j is the larger child. If the parent node is greater than or equal to larger child, then the heap is correct. I mean that is the correct heap. So what we have to do is we have initialized this some flag kind of variable heap. We will assign heap to true now. Heap to true. Okay. If not, else. Okay. Fine. So if v, I mean this element, so if the 15 greater than 25 is condition true, false. Therefore what you did, you pushed element 15 to this position, isn't it? Therefore you have to change h of k to h of j. I mean you have to assign this element h of j to h of k. You have to assign the element 25 to the element at index k. So that is what h of k is equal to h of j. Okay. So once you have moved 15 to here and 25 here, 15 here, what you did? So once again you have to check this node whether it is a heap. Whether it is a heap. That is why what you have to do is now k value was 3. Now you have to change k value to this. And how do you obtain this value? This is nothing but j. That is nothing but j. Yeah. Therefore h of k is equal to h of j and k is equal to j. And k is equal to j. So that after pushing again we consider this node and we recursively go on checking whether it is a heap. Okay. Right. Done. So that is why there is a while loop also. Now, so h of k is equal to h of j and k is equal to j. Right. Done. This is all fine. So in this case k is equal to j. Now k becomes 6. K is equal to 6. Next again go to while not heap. While not heap, I mean still heap is false, because v greater than h of j does not hold good. Therefore, and 2 into k less than or equal to n. Now what is the value of k? K value is now 6. 2 into 6 is 12. Is 12 less than 7? Condition fails. What do you mean by 2 into 6 less than or equal to 7 condition fails? That means that the element that we are now considering is a leaf element. It is not a parental element, and hence we need not to check for whether it is a heap. Right? Whether it is a heap. Done. Alright. Now, so finally what we have to do is h of k we have to assign the element v. So the k value, what is k value? That is 6. That is 6, right? So see after doing so, k is equal to j. So here in this case what we did, the h of j we assigned to h of k, right? Therefore the node at j is still need to be replaced, isn't it? And that value in this case is nothing but 15. And after this what did we modify? J value we modified to k. Therefore at the end we have to modify h of k to v, so that we will be now assigning the value 15 to h of 6. Okay, h of 6 is nothing but this, and hence the tree now, the heap now takes this form. So here h of k, that is 25 we made, this is 12 and 40, and this was still pending, we are not yet replaced after this, and hence this is still pending, which is nothing but 15 now. And how do you obtain 15? It is v. V is h of k, right? And that is how the algorithm moves on. So now you have to trace the algorithm similarly for this element and similarly for this element. Trace the element, trace the algorithm for the element at index 1, so that all the steps will be clearly understood. Okay.